Hello friends, welcome to CEC live lectures. I am Dr. Pavitra Bharadwaj and I am Associate Professor in the Department of Computer Science in Jesus and Mary College, University of Delhi. So friends, we have been talking about different aspects related to operating system in this series of our lectures. And in today's lecture, we are going to talk about another very interesting topic related to operating system and also otherwise of very common interest, that is threads. So what is a thread basically? A thread is a basic unit of CPU utilization, right? So it is that program or that code which is being executed in the CPU at any given point in time. A thread will always have a thread ID, it will have a program counter, it will have a register set and it will have a stack of its own. So a thread needs these four elements: an ID, a program counter, a register set and a stack. So earlier in traditional processes we had seen that there were single thread of control. That is a process will only have a single thread, and if a process is executing, it means the single thread is executing. But now with time, as the technology has evolved and how changes have taken place, so now we can see that a process can have multiple threads of control. That is, it can perform more than one task at a time. Earlier it was uni-thread systems. Now we are talking about multi-threading system where one process or one task can be divided, one application can be run over multiple threads. So therefore threads are very, very significant, and they have actually revolutionized how the processing is happening and how computers' performance has been enhanced over the time. So if we see here in this diagram, it shows a single threaded process compared to a multi-threaded process. So if we see in a single threaded process, we have only a single thread which is executing, and it has its own code, data and stack, registers, etc. It has its own files, right? Whereas in case of a multi-threaded system, all the different threads of the process, they are going to share the code, they are going to share the data, they are going to share the operating system files, and each thread will have its own stack and its own registers. So part of the resources are shared and part of the resources belong to the thread alone. But we can see that this can give us many advantages. Use of multiple threads in a process can give us multiple advantages. It can it provides multifold benefits, right? So what is the motivation? Why should we be using this kind of atmosphere? Why we should be having processes which are multi-threaded processes? So now we know that most modern computer system, they support this kind of a architecture. The hardware actually supports this kind of a multi-threaded architecture. Any application which is implemented as a separate process with several threads of control, every application which is now being run, it is created in a way, it is designed in a way that it can be divided into multiple tasks, and each task can have its own, that is, task means it will have its own thread. Like for example, we have the simplest example of say Word, a text editing application program. Now in this we can have 3 threads or even more threads for that matter. So one thread is controlling the keystrokes which the user is putting in, the other thread is saving the application, the third thread is maybe helping the user with spelling and grammar checking. So these are 3 different tasks, 3 different threads which are running at the same time. Likewise if we have a browser, now browser is a single application. Now it can have one thread which is displaying images or text, etc. Another thread is there which is retrieving the data from the network. So there are different, all applications these days are typically multi-threaded applications because they can have multiple lines of control. Then applications, besides they are designed this way. Why are they designed? Because the systems are now becoming multi-core system. We will be talking about what a multi-core system is. So we have the processing capabilities, the CPUs are very advanced, and in order to leverage this kind of capability we need to have applications, and these applications can perform several CPU intensive tasks in parallel across multiple computing cores. So now the performance problem of the CPU that is being overcome by using these multi computing cores and using multi-threaded architecture. Now process creation, basically when we used to talk about process creation, earlier operating system, they used to implement each application in the form of a single process. Now when we say process, so a process creation is a time consuming and resource intensive task, right? So and if the new process which is being created is going to perform the same task as the existing process, so then what is the need for that extra overhead, that why should the system give precious resources for that kind of a process which is already executing, a similar process is executing. However, on the other hand, creating threads is much lighter, it is more efficient and therefore it is always better to use a process that can contain multiple thread instead of multiple process which are running at the same time. So threads, they are also very important in the remote procedure call system, which we had seen in the last lecture, that we have RPC systems where individual processes are communicating. So RPCs will allow inter-process communication and they provide a communication mechanism which is similar to ordinary function or procedure call. So we can have a designated thread which is looking at the procedure, the communication between the two processes which are running to each other. So RPC servers, they are generally multi-threaded server. So whenever a server will receive a message, it services the message using a separate thread, and this allows the server to receive several concurrent requests. So it is not the same process which is accepting the request and processing it. There are two threads, one is accepting the request, the other is processing the request. So therefore concurrent request management can be done, and most of the operating system kernels these days, they are multi-threaded kernels. So there are several threads which they operate in the kernel, and each thread performs a specific task. So we have one thread for managing the devices, there is another thread for managing memory, another for interrupt handling. So different functions of the operating system are also executed using different kinds of threads. So there is no doubt why multi-threading environment or why multi-threaded processes should not be used, because we have the hardware support, we have the application support, and we have got the operating systems which are designed in ways so that they support this kind of architecture. Besides this also the multi-threaded programming, it is very advantageous. The benefits, the four important benefits of multi-threaded programming are responsiveness, resource sharing, economy and scalability. So first and foremost is responsiveness. Responsiveness means that if one process is down, then also the system remains responsive, the system keeps on going. So when we are talking about multi-threading, an interactive application which allows a program to continue running even if part of it is blocked or is performing a lengthy operation, thereby increasing the responsiveness to the user. So the quality, this particular quality of responsiveness, it is very important when we are designing user interfaces, right? For example, if we have a button, if the user clicks on a button, and this button clicking will result into a very time consuming operation, right? So if it is a single threaded operation, or if it's a mono thread operation, then the user will have to wait till the time this operation is completed. But in case of a multi-threaded environment, the time consuming operation is performed in a separate thread and the other part of the application will remain responsive to the user. So, therefore, we can use the multi-threaded programming for creating a very responsive user experience, responsive user interface. Another aspect, another very important benefit of multi-threading is resource sharing. Now, we had seen that processes can only share resources through techniques like shared memory and message passing, right. So, these techniques, they are explicitly arranged by the programmer, but when we are talking about threads, so the threads, they share the memory and the resources of the process to which they belong by default. We had seen that each process will share the data, the files which are belonging to the process to which the thread is belonging. Then this benefit, and they also share code and data, right. So, this allows application to have several different threads of activity within the same address space. Another important benefit is economy. When we are saying that resource sharing is taking place, so it is also leading to economy. How? Because allotting memory and resources for process creation is costly. We have already seen that there is a lot of overhead which is involved when new process is created. But now, because thread is only sharing the resources of the process to which they belong, so it is more economical to create and context switch thread. So, once a process is created, then there is no need to create another processes, you can only create multiple threads. So, whatever resources have been given to that process, they can be utilized by the threads which are created by this process. So, it is not easy to calculate and predict how much overhead is saved, but definitely creating processes is much more time consuming, managing processes is much more time consuming than creating the threads. Another important benefit is scalability, because we know that we have multiprocessor architecture, right. So, we can have threads which are running in parallel on different processing code, whereas if you have a single threaded process, then it will only run one thread on a single processor. So, even if you have multiple processor, you are not utilizing those multiple processors because you have only a single threaded process, whereas the multi-core processors can be leveraged to the utmost, to their best, if you are using a multi-threaded environment. Now, because when we are talking about multi-thread, it is very important to understand what is multi-core programming, right. So, in response to the computing power or the need for enhanced computing performance, the single CPU systems, they evolved into multi-CPU system. Now, we say it is a multi-processor, right. Why are we saying it is a multi-processor? Because on the same chip, there are multiple computing cores which have been designed, right. So, each core will appear as a separate processor to the operating system. So, you can have tens to hundreds to even thousands of cores, thousands of processors which can be incorporated in a single chip, right. So, whether the cores now these appear across the CPU chips or they are within the CPU, within the single CPU chip, we call these as multi-core or multi-processor system. Multi-core or multi-processor means that you can have more than one processor at a given time. Now, multi-threaded programming will provide a mechanism which is more efficient use of these multiple computing cores and improved concurrency. It is very important to understand the difference between parallelism and concurrency. Now, a system can be parallel if it can perform more than one task simultaneously, right. And if you can say that a system is a concurrent system when it supports more than one task by allowing all the tasks to make progress. That is, we are saying that there are multiple tasks which are executing, but it is only an experience, it is only a feeling which is given to the user that all the tasks are moving because you are using the time interleaving format. So therefore we can say that you can have concurrency without having parallelism. Parallelism simply means that all the tasks, all the processes, they are running parallel to each other, whereas in concurrency one is stopped to run the other. So all the tasks are progressing together. When most computer systems, they have a single processor, so that time CPU schedulers were used, they were designed to provide the illusion of parallelism, right, that is known as concurrency. So they are concurrent but they are not parallel. Right, now after we have evolved and after we have these multi-core systems, then we say that we have actually achieved parallelism, because we can have tens of hundreds of thousands of threads which are running on different cores of the CPU parallelly. Right, now it is not very easy also to program the program for this kind of a multi-core processor, or to create this kind of algorithms which can run on multi-core processors, right. So for this also the programmers, they face a lot of pressure, the designers and the application programmers, they have to write algorithms, they have to write programs so that they can have the best use of multiple computing cores, right. So they have to, and also the designers of operating systems, they also need to write scheduling algorithms that can use these processing codes to allow parallel execution. So this is a challenging aspect of multi-processor systems. There are 5 basic areas in which these programming on multi-core systems, they pose a challenge. So first challenge is to identify the task. That is, the programmers, they have to identify, they have to examine applications so that they are able to find areas which can be divided into separate concurrent tasks. That is, the tasks which are independent of each other, and therefore they can run in parallel on individual cores. So they need to identify which are the tasks which can be run parallelly on the different cores. Second is to create a balance. So when they are identifying the tasks which can be run in parallel, they also need to ensure that each task which is being assigned a core will do equal work of equal value. Say some task, it may not contribute as much value to the overall process as the other task. So in this case, it is not viable to assign a separate CPU core to such a task. So striking this balance is also very important for the application and the system programmers. Then also to split the data. Now we say that the application is split to separate the tasks which can run parallelly. Likewise, the data which is accessed and manipulated by the task, it also needs to be divided so that it can run on separate cores. Then there can also be a situation where there is a dependency of data between the different tasks. That is, the output of one task is required as an input by the other task. So in this case, the programmers, they have to synchronize and to accommodate this kind of data dependency. They have to schedule the tasks in such a way that even though they are running parallelly, the data dependency is taken care of. Also, it is very important and very difficult to test and debug the applications, the programs which are running in parallel on multi-cores, right, because there can be many different execution paths. So these are the debugging of such programs is much challenging as compared to single threaded application. But nevertheless, even though these challenges are there, still this kind of multi-core processing or multi-threaded programming is gaining a lot of hype, and it is being used very commonly, right. So now we see that there are 2 types of parallelism which is witnessed commonly. One is data parallelism and the other is task parallelism. So data parallelism means that the focus is on distributing the subsets of the same data across multiple computing cores and performing the same operation on each core. Like for example, if we have to sum the n elements of a of an array, say for instance. Now in this case what we can do is that we can divide the n elements of the array and we can assign the 0 to n minus 1 upon 2, that is half elements of the array to one core and the other half to another core. So both the cores are doing the same operation, but they are working on different sets of data. Whereas if we look at task parallelism, in this we are not distributing the data, but we are actually distributing the task or the thread across multiple computing cores. Now in this case each thread is performing a unique operation. So different threads may be operating on the same data or they may be operating on the different data. For example, we are using two different statistical functions on the elements of an array, right. So different, the data is the same elements, but you have two threads which are running on two cores. One is calculating say the standard deviation and the other may be calculating some other statistical function. So therefore this is called task parallelism, in which the task is divided or the task is distributed among the different cores. Now multi-threading models, multi-threading can be executed in different forms, right. So basically we have two types of threads. We can have a user thread which is at user level and we can have a kernel thread which is at the kernel level. Now user threads, they are supported above the kernel and they are managed without the kernel support, right, whereas kernel threads, they are supported and managed directly by the operating system. So basically all contemporary operating systems like Windows, Linux, Mac, etc., they all now support the kernel threads. Now multi-threading, there can be relationship which exists between the user threads and the kernel thread. So there are three common ways of establishing the relationship between the kernel and the user thread. So first type of model which defines the relationship between kernel thread and user thread is many to one model. We can have a one to one model and we can have a many to many model also. Now the name itself suggests that how the user thread is bound to the kernel thread. So in the many to one model there is the multiple user level threads, they are bound to one kernel thread, right. So thread management in this case is done by the thread library in the user space. Thread library basically is another topic which we can take in another lecture. So it is very efficient because the thread library in the user space is managing this kind of thread allocation. Now but the problem here is that because multiple user threads, user level threads, they are connected to a single kernel thread. So if one thread, it makes a blocking system call, then the entire process will block, right. Also because only one thread can access the kernel at a time, so multiple threads are unable to run in parallel on multi-core system. So basically we are losing on the advantage of having multi-core system because only one thread is running at a given time. So this diagram shows how multiple threads of the multiple user threads are bound to one kernel thread. So now this many to one model is not very commonly used because it does not leverage on the multi-core programming. The next model is one to one model, in which each user thread is mapped to a single kernel thread. So it provides more concurrency than the many to one model by allowing another thread to run when a thread makes a blocking system call. So therefore this allows multiple threads to run in parallel on multiprocessor. So one to one model is commonly used in operating systems like Linux and Windows, etc. It is a popular model. The only drawback which this model shows is that when you are creating the thread, then every time a corresponding kernel thread has to be created. So there is this overhead of creating kernel threads which burdens the performance of the system, right. Other than that, the one to one model is a successful model. Then we have the many to many model, in which you have multiple user threads which are mapped to smaller or equal number of kernel threads. So, if you have say 10 user threads, so then you can have say 6 or 7 kernel thread. So, the number of kernel threads is specific to the application, or it may be to a particular machine, how many kernel threads are there. So, we know that in many to one model, you can create as many user threads as you wish, the user can create, right. It does not result in concurrency because only one thread will be used. In one to one model, it allows for greater concurrency because you have to, we have to be careful that you cannot create too many threads within an application. So, the many to many model, it suffers from neither of these two shortcomings, that is, the developers can create many user threads as necessary and the corresponding kernel threads can run in parallel on the microprocessor. So, besides this, there is another model which is called two level model, in which a user in which you can have multiplexing at user threads to smaller equal number of kernels, and you can also have a user level thread which is bound to a single kernel. So, you can see in this diagram, you can have multiple threads which are bound to multiple kernel threads, and you can have a user thread which is bound to a single kernel thread also. So, friends, this was all about multi-threading and multi-core programming. We shall be continuing our discussion. Till then, keep watching CEC. Thank you.